Okay, sulfuryl chloride, SO2Cl2, is used as a source of chlorine. We consider a reactor operating at steady state, performing a decomposition reactor in the gas phase. 1 mole of sulfuryl chloride goes to SO2 and chlorine. Okay, the question is, if pure sulfuryl chloride is fed in the reactor at a flow rate of 50 pound-moles per hour, and the reactor output flow rate is 80 pound-moles per hour, what is the extent of the reaction? What is the molar flow rate of each component in the reactor output stream? And then
there's some of the sulfur chloride right now. I just put positive CO2.
look louder.
There's some of those coming out as well as SO2 and CO2.
SO2 and Cl2. Okay, does everybody make sense for the picture? What's your system? Reactor. It's pretty easy, great. Okay, and units, pound-moles per hour. And then we put some variables on this. Let's see, I might label some streams, 1 and 2. And then maybe I call this A. This is A coming out, maybe call this B and C, and maybe just keep it real simple. Got a couple of flow rates we can put on here, right? So let's see, flow rate going in, N1 dot is 50 pound-moles per hour. N2 dot is 80 pound-moles per hour. Okay, so I've got total molar flow rates, N1 and N2. And what do I want to know? What is the extent of reaction? I want to know psi dot. And I want to know the molar flow rate of each component in the output stream. So I want to know A2 dot, NB2 dot, and NC2 dot. All right. Total mass balance is what I want, or total molar balance is what I want to do here. Anybody get some mole balances written? Great. So accumulation A is 0 because steady state. A in minus A out plus A gen consumption, which we'll use this new formalism. UA times psi dot. Great. There's an equation for A. How about B? There's no B in, there is B out, N dot B2 plus nu B psi dot equals 0. And then C, I can also do the same thing. 0 equals opposite NC2 dot plus nu C psi dot. Questions how I get those? So this is out, minus out plus reaction is 0. What's nu A? Nu B and nu C? Let's see, nu A. So A is sulfuryl chloride, is the reactant. It's going to be minus 1. The other two are products. The stoichiometric coefficients there are both 1, so these are both just plus 1. So we've got a minus, a plus, and a plus. That's great. So we can go ahead and we can solve these. We've got 1, 2, 3, 4, 5 unknowns and 3 equations. But I've got a couple flow rates, so I can put those in. I can probably solve those. So let's see. N dot 1 is N1A dot plus, yeah, that's it. It's N1A dot. One equation, like this guy over here, is NA2 dot plus NB2 dot plus NC2 dot. Great, so now I've got 5 unknowns, 5 equations. I should be able to crank through this and solve this. The other thing I can do is use my total mole balance. My total mole balance can be very handy here. dN dt total moles in the system isn't going to change. That's going to be 0 equals molar flow rate of 1 minus molar flow rate of 2 plus, actually, N, A, and B. There's actually 3 species here, A, B, and C. We sum mu A plus mu B plus mu C times psi dot. This is minus 1 plus 1 plus 1. This is going to be N1 dot minus N2 dot plus psi dot equals 0. I could also get that same equation from adding these guys up. Here, 0 equals NA1 is the same as N1 dot. And A2 plus B2 plus C2 is N2 dot. And minus psi plus psi plus psi is plus 1 psi dot. All right, that equation makes it really easy for me to solve from the data given. And 1 dot is 50 moles, 50 pound moles per hour. And 2 dot is 80 pound moles per hour plus psi dot equals 0, which I'm plugging into this equation. Put those to the upper side, and I get 30 pound moles per hour psi dot. And there's my extended reaction. From that, I can plug in the material balances. I should be able to go the other flow rates. What's new here? We use psi dot. We're using mole balances. We're using both component mole balances and total mole balances. There's actually 3 independent equations here. If we do our degrees of freedom, every material balance for each component gives us an equation. There's 3 independent equations. This one's not independent. It's just a combination of the other 3, but we could use this one. It's just mean one of these will be redundant. So if we choose to use this, we might be able to use 2 of these others to, and we'll solve everything from 2 of the equations. So you get to use n equations for n components. You can pick any of them, including the total or not. Okay, so I've got some general system, and what I want to do is I want to think about a system that maybe has multiple inputs, and maybe has multiple outputs, and maybe has many species inside it, A, B, C, etc., and maybe has many reactions. A plus B goes to C, B plus F goes to G plus H, etc. So I want to talk in general. Let's say there's many reactions going on, many inputs and many outputs. Many components, streams, and reactions. Kind of like what you might have to say in a biological cell. Many things going on, many things going in, many going out. Lots to keep track of. Okay, so how are we going to do this? I want to label each component I. So I want to have A, B, C. I represent component A, B, C. Have the streams labeled as J. And have the reactions labeled as K. And then I want to do my material balances again. Total mass balance. Let's see, so I want to do accumulation equals in minus out plus gen minus consumption of total mass balance, dm dt. Okay, the change of the total mass in the system with time. So I have multiple streams coming in, so I'm going to have to add all of those up. So I used to have M dot for the input, but now there's multiple streams going in. So I'm going to sum over all streams J going in. All of the streams going in, I have to sum up their mass flow rates going in. Same thing for those going out. I need to sum over all J going out, the mass flow rate of each stream Mj. And then how about generation and consumption of mass, total mass? Can a generator consume mass in the system? Not unless I have a nuclear reactions, so there's +0 for that. Okay, so here all I've done now is label each of these streams coming in. Now if I want to do the component mass balance, I want to look at dm sub I dt, so component I, which could be A or B or C. It looks the same actually. I'm going to sum over all j streams in. Now instead of just m dot j for stream j, I also want component I. So I want m dot ij. Component I in stream j. So this is stream 1, 2, 3. I have how much A is coming in stream 1, plus how much A coming in stream 2, plus 3. And I've been looking at the outputs also. So then on the outputs, I'll subtract all streams j out. M dot ij for output streams. So all the mass coming in, all the mass coming out of component I. Now generation and consumption, I have reactions. So if A is consumed in reaction 1, I need to take stock of that. So I'm going to add to this reaction K, psi dot K. So instead of having just psi dot, I'm going to label it for each reaction. Maybe I'll have 4 reactions in a smelter. I'll have psi 1, 2, 3, 4. To get it to mass, I take the extensive reaction, I multiply by the stoichiometric coefficient of species I. So that's how much A is produced or consumed by reaction K. Then that's going to be in moles, and I need to get it to mass. So I have a molecular mass, component I, and then I'm going to sum this over all reactions K. So I term for each reaction that looks like a molecular mass, stoichiometric coefficient, and the extent of reaction. Also going to call this sum over all reactions K of R I K, R dot. So if you remember, we're using R as a mass rate of reaction. How much mass of I is created by reaction K? We call that capital R. That's R. I is mi nu I k psi dot k. What happens to these equations at steady state? 0, what's 0? These guys at the left here, this is 0, it's at steady state. And that's 0 at steady state. So if we're at steady state, I'm just going to have mass in minus mass out equals the sum of all reactions. And I won't have to have the accumulations, right? Great. How about in moles? Now again, for moles, I'm going to take the components, I'm going to convert this to moles, and then I'll add them together to get the total. So the component mole balance. I really just want to take the mass of I, the change of mass of I in the system per time. If I divide that by the molecular mass, capital MI, I'll get, so if I take MI divided by capital MI, I'm going to get NI. That's also true for MI dot stream 1. If I divide by MI, I get NI dot in stream 1. If I do that with each, if I divide through by the molecular mass, we'll get dNi dt, the change of the moles of species I in the system. It's going to be the sum of all the flow rates in, sum over all streams j in, Nij dot. So that's the moles of species I in stream j coming in. I'm going to subtract the outs. Subtract over all j out. N dot ij. But you guys asked for a theory first. Okay, and then the reactions, I'm going to take this term here and divide by capital M, which is already there, and that's just means I'm going to have a sum over all reactions K of nu ik psi dot of k. Or I could call that sum over k of little r I k dot, where r I k dot equals nu I k psi dot k. And if I sum these, sum over I, d and I, so if I take the moles of A plus the moles of B plus the moles of C plus however many species I have, I can get the total dn dt, so n is the sum of n sub I over all I. So we have n dot, say if n dot of j is the sum of n dot ij over all i's. So the total number of moles in the system is the sum over all streams j in of n dot j. N dot j is the total of everything in stream j, all the components I. Subtract the sum over all j out, n dot j, plus, and now I've got to sum all of these reactions. I can distribute out the xi k, and it's going to turn out to have the sum of sum over all reactions k. And then for each reaction, I'm going to have mu in the first species plus mu in the second species. So I'm going to sum over all components I mu I k. So that's reaction 1, nu A plus nu B plus nu C, etc. And then I'm going to multiply that by xi k dot. Okay, manufacture of urea. This is following on the ammonia theme we've been having in class. We're taking ammonia, we can make urea out of it, and urea is a good fertilizer. It's liquid and safe. So we want to take NH3 and CO2 and make ammonia and water. The second bullet, how do we make it? 2 gas streams, one at 100 gram moles per minute, containing 80% by moles ammonia and 20% CO2. The other at 50 gram moles per minute, containing 90% CO2 and 10% H2O, are mixed and fed to a reactor operating at steady state. Inside the reactor, ammonia is consumed at a rate of 68 gram moles per minute. Find the flow rates of each component out of the reactor as well as the total flow rate out. So this is a typical problem. We'll be given some inputs, some criteria, some about the system, and then you want to know all the flow rates. We've got multiple ins, we've got multiple species. What do we do first? Draw a picture. Okay, draw a picture.
Yeah, I have ammonia and CO2 going in on the top one. And then CO2 and H2O going in on the bottom. And then all the components
All the components being
every single one.
ammonia, CO2, water,
Yeah.
and what's our system?
Reactor.
Reactor. Okay, and remember we used to question, yeah.
Should urea be in the output stream as well?
Yes. Urea in the output stream, product there. But step 2, define a system. Step 3, choose components. Components, atoms, composites, or compounds? Everybody? Compounds. Define stream variables, number streams, stream 1, stream 2, stream 3. Convert all numerical information into consistent units. Do we have consistent units? Gram moles, great. Define a basis. Actually, what if we use our new nomenclature that we have from this derivation and put these numbers on there, all the numbers we have up there. 100 gram moles per minute, what do we call that? What variable is that under that new system?
And one dot.
N, what'd you get? N1 dot, 100 grams per minute. Great. What else? 80% NH3. What do we use for mole percent composition? What variable? X. So X1 of ammonia is 80%, X1 of CO2, 20%. All right, stream 2, 50 grams per minute. N2 dots, 50 grams per minute. And those compositions there too. 90% CO2. X2C is 50% and X2W is 50%.
Yeah, it's 90-10. It's 90-10.
90-10. Where do I get 50%? Just want to make sure you're with me. 90% CO2? Okay, so I was on a defined basis, but really just filling out all these numbers I have. What else do we have? Ammonia is consumed at a rate of 68 gram moles per minute. What's my variable for that? About our ammonia dot minus 68 gram moles per minute. This is our dot, our net reaction rate. There's one reaction, so we don't need multiple reactions in the case. We're going to need one extensive reaction. So let's see. So we're going to have RA dot. If we define that in terms of extended reaction, what's RA dot in terms of extended reaction? Ammonia is getting consumed, so UA times xi dot is going to be minus 1 xi dot is minus xi dot. Yes. So actually this, right here we know that, so we'll have 68 gram moles per minute is xi dot. And I think at that point I'm going to leave her steps alone, and from there I should be able to write material balances. I would just do a material balance on, sorry I'm taking too long here. Material balance on ammonia. Accumulation equals ins. I've got ammonia coming in, N1 ammonia dot plus N2 ammonia dot minus N3 ammonia dot plus our ammonia dot. Two inputs, one output, the reaction rate. I could do this for the 3 species and I can plug things in and go.